This lesson will serve as a review of week 16 and the concepts that we covered, which were the Lewis electron dot structure, identifying cations and anions, putting together an ionic compound, and then lastly we talked about something that we called the crisscross rule. Lewis electron dot structure. A Lewis electron dot symbol is a symbol in which electrons in the valence shell of an atom or ions are represented by placing dots around the atomic symbol of the element. The dots are placed one to each side of the elemental symbol until a dot is placed on all four sides of the elemental symbol. Then the dots are written two to a side until all of the element's valence electrons are accounted for. For instance, boron has 3 valence electrons. Its Lewis electron dot symbol would look like this. You draw the atomic symbol for boron and then place boron's 3 valence electrons around boron's atomic symbol. This electron dot symbol, however, is not representative of boron's electron configuration, which is bracket helium 2s2 2p1. Perhaps a better representation would be something like this. And this representation shows that boron's electrons in the 2s subshell are paired, and its electron in the outer 2p subshell is unpaired. This first symbol, however, is the correct Lewis electron dot structure for boron, since all 3 of boron's electrons are actually involved in chemical bond formation. So let's do an example of the Lewis electron dot structure to represent the electron transfer between magnesium and a fluorine atom. The chemical reaction between fluorine and magnesium looks like this. 2 fluorine plus 1 magnesium yields magnesium fluoride. So 2 fluorine atoms, the Lewis symbol for fluorine looks like this, combine with 1 magnesium and what's occurring is magnesium is donating its 2 electrons to each fluorine atom. The end result each fluorine has gained an electron and now has 8 valence electrons. Magnesium has lost both of its electrons, so it now has a positive charge, 2 plus. And in order to satisfy this 2 plus charge, the ionic bond has to be between 2 negatively charged fluorine atoms. Identifying cations and anions. The basic process that occurs when an ionic bond is formed is a metal loses an electron and a nonmetal gains that electron. And when this occurs, cations and anions are formed. These cations and anions are attracted to each other because of the electrostatic attractive forces between positive and negative charges. These opposite charges bring these ions together to form an ionic bond. The main concept to remember is that a metal reacts with a nonmetal to form an ionic bond. In general, we can determine the charge an ion has based on its position on the periodic table. For instance, group 1A, the alkali metals tend to form +1 charges. They do this by losing the single electron from their outer ns1 orbital. For instance, the ionization energy that is required to remove sodium's electron from its 3s orbital is 496 kilojoules per mole. Now, to remove a second electron from sodium requires an energy input of 4,562 kilojoules per mole. And this is because the second electron would need to be removed from sodium's stable noble gas core. In ordinary chemical reactions, enough energy is supplied to remove valence electrons, but not generally electrons from an atom's stable noble gas core. The group 2A and 3A elements tend to form +2 and +3 cations. Removing of magnesium, which is a 2A element, and aluminums, which is a 3A element, electrons, in order to form a Mg2+ and Al3+ cation respectively, is easy compared to removing electrons from either of these two ions. And this is why elements do not tend to form ions that are greater than their group number, just because it requires tremendous amounts of energy to remove an electron from an element's stable noble gas core. So elements in general do not form ions that are greater than their group number. Groups 6A and 7A on the periodic table have the largest electron affinities. Thus, we would conclude that these elements tend to form monatomic ions by gaining electrons as opposed to losing them, because remember, electron affinity means that they want electrons. They have an affinity for electrons. Group 7A, the halogens, have 7 valence electrons. The halogens therefore gain a single electron in order to fill their valence energy level, giving them an overall -1 charge. Examples include fluoride, F-, and chloride, Cl-. They're both members of the halogen family. Hydrogen also forms a -1 ion, H-. The hydride ion has an electron configuration 1s2, and this is equal to helium's electron configuration, which is one of the noble gas elements. An atom that is a member of 6A tends to gain 2 electrons, giving them an overall -2 charge. Examples would be O2-, an oxide ion, and S2-, a sulfide ion. Now, it's interesting, the electron affinity for nitrogen may be equal to 0, but it actually forms a stable N3- nitride ion in the presence of certain positive ions, such as lithium and other alkaline earth metals. So, to summarize, cations that belong to groups 1A through 3A that have noble gas or pseudo-noble gas cores tend to form cations that are equal to their group number. So the alkali earth metals are part of group 1A. They all form +1 cations. The alkaline earth metals are part of 2A. They all form +2 cations. Cations that belong to groups 3A and 5A with electron configurations ns2 form ion charges equal to their group number -2. Examples would be titanium, which is a member of group 3A, forms Ti plus, because it's part of 3A, 3 minus 2 is 1. Tin and lead are both members of groups 4A. 4 minus 2 is 2, so they form +2 cations. Then bismuth is a member of group 5A, so it forms a +3 cation. 3. Anions that belong to groups 5A to 7A with pseudo-noble gas core electron configurations form ions that are equal to their group number -8. So for instance, the halogens are members of group 7A. 7 minus 8 is -1. The halogens all form -1 anions. This table shows common monatomic cations and anions. So let's just go through it sort of briefly here. Group 1A, the alkali metals, all form cations with +1 charges. Group 2A also form cations, but instead of being +1, they are form +2 charges. And the way that you remember this is the alkali metals are part of group 1A, and the alkaline earth metals are part of 2A, so they form +2 charges, and the alkali metals form +1 charges. Silver is a transition metal. It tends to form an Ag+ ion, +1. Zinc, also a member of the transition metals, tends to form a zinc 3+ cation. Group 3A, boron doesn't tend to form a cation at all. But silver and gallium and indium all form 3+ cations. Titanium forms a cation equal to its group number -2. So titanium forms a +1 cation. Group 4A, carbon, silicon, and germanium, none of these guys form cations. But underneath of them are two metals, tin and lead. They form 2+ cations. The group number 4 minus 2 is 2. Nitrogen and phosphorus, part of group 5A, tend to form 3- anions. Arsenic and antimony don't tend to form anions at all. Bismuth, all the way down at the bottom, is a metal, and he forms a 3+ cation. All of the nonmetals and the metalloid in group 6A all form ions equal to their group number 6 minus 8, which is -2. So oxygen, sulfur, selenium, and tellurinium all form -2 anions. And of course the halogens, which are group 7A on the periodic table, all form -1 anions. As well, hydrogen has the ability to form a -1 anion as well. So this table, it's probably best that you make some flashcards and memorize it, but know that a lot of cations and anions can be determined based on their group in the periodic table. Putting an ionic compound together. So let's say you wanted to know the formula for a compound. Say the result of reacting magnesium and bromine together. You begin by putting both atoms side by side, with the metal on the left and the non-metal on the right. And we write the electron configurations for both atoms. Magnesium's electron configuration is 1s2, 2s2, 2p6, 3s2. Because its atomic number, Z, is equal to 12. Bromine's atomic number, Z, is equal to 35. Thus, its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. But in this context, it's probably more appropriately written with 4s2 and 4p5 at the end of the electron configuration instead of writing it in the fill order, because the valence electrons are in 4s2 and 4p5, and these are the electrons that are going to be involved in our chemical reaction. Magnesium is an alkaline earth metal, a group 2A element, which means it has 2 electrons to lose to form a cation. After losing those 2 electrons, its resulting cation will be Mg2+. And its electron configuration is now 1s2, 2s2, 2p6. Bromine is a halogen. It's a member of group 7A, and it has 7 valence electrons. Bromine, like chlorine, would prefer to gain 1 electron as opposed to losing all 7. After gaining an electron, its resulting anion will be bromide, Br-. And its electron configuration can now be written as 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, and this should be 4p6, not 4p5, because now its outer p orbital is filled. Now, in order for our compound, magnesium bromide, to be neutral, it must have the same positive and negative charges so that its overall charge is equal to 0. Since our magnesium cation has a charge of 2+, we will need 2 bromide ions in order to balance its charge. The resulting compound is thus MgBr2, magnesium bromide. Crisscross rule. A quick way to determine or check the formula for a compound is to apply something called the crisscross rule. This rule uses the ion's charge in order to determine the formula for the resulting compound. The way it works is you take the numerical value of the metal ion's charge and you move it to the bottom of the right-hand side of the non-metal symbol as a subscript. Then you take the numerical charge of the non-metal ion's charge and you make it the subscript for the metal. So in the case of magnesium bromide, the compound's formation, magnesium's charge value is 2. This becomes bromine's subscript. And bromine's charge value, even though we didn't write it, is -1. This becomes magnesium's subscript, and you obtain the formula simply as MgBr2. Let's demonstrate the crisscross rule visually so you can see what's actually taking place. A magnesium cation has a 2+ charge. A bromide anion has a -1 charge. The compound that it forms is magnesium bromide. The metal is on the left and the nonmetal is on the right. So we take magnesium's charge value and we make it a subscript for bromine. We take bromine's charge value and we make that the subscript for magnesium. But since it's 1, we don't actually write it. So our compound is magnesium bromide, MgBr2. The formation of compounds involving polyatomic ions can work the same way. Take, for instance, a compound involving both ammonium and sulfate. We write ammonium, we'll actually write out its charge value. It's actually +1 instead of just putting a plus. And sulfate, its charge value is -2. Ammonium, we take the charge value of sulfate and we put it outside of the ammonium ion. We take the charge value for ammonium, which is just simply 1, and we put that outside of sulfate, but since it's only a 1, we don't need to put parentheses subscript 1. We just put SO4. We just write the sulfate ion. So we know that in order to satisfy sulfate's -2 charge, we will require 2 ammonium ions. The crisscross rule works very well most of the time, except when it doesn't. So let's say you wanted to react calcium and oxygen. Calcium is an alkaline earth metal that forms a 2+ charge. Oxygen forms an anion with a -2 charge. So applying the crisscross rule, we would get the formula Ci2O2. But this formula, however, is incorrect. So after you apply the crisscross rule, you must divide by both subscripts by a common denominator. In this case, the common denominator is 2, so the correct formula for calcium oxide is just CaO. To conclude, this week we investigated a way to represent ionic bonds and transfers of electrons between two atoms. The Lewis dot symbol gives us a way to represent valence electrons around a given atom. The dots are placed one to each side of the elemental symbol until a dot is placed on all 4 sides. Then the dots are written 2 to a side until all electrons are accounted for. This gives us a simplified way in which to think about valence electron transfers during ionic bond formations. We also investigated how we can determine the charge of an ion based on its position on the periodic table. Cations tend to form ions equal to their group number, whereas anions tend to form charges equal to their group number -8. Cations tend to be metals, whereas anions tend to be nonmetals. The main concept to remember in ionic bond formation is that a metal transfers an electron to a nonmetal, then the resulting cation and anion are held together by electrostatic attraction forces. Lastly, we talked about how to put together ionic compounds based on their respective ions, and we introduced a technique called the crisscross rule. This can be used to determine the formula for most ionic compounds. In our next lecture, we will begin looking at covalent bonds, which shouldn't be too difficult to understand if you have a decent understanding of ionic bond formations.